Hello, let's hear it for a sociable welcome. On the count of 3, turn to your neighbor and say hello. There are no strangers here, only friends we are yet to meet. First of all, the reason we're standing here is about to share our E1 experiment, which is half and full wave rectifier. I hope this could help you to improve your understandings. Here's a healthy welcome, big and warm enough, to our beloved lecturer, Dr. Norain Hussein. For your information, we were taking this experiment on 11 January 2022. This is us, our team during this SEM. You can look our rating scale. We cool, right? For us, if you want to lift yourself up, lift up someone else. Without further ado, let me share more about this experiment. The objective of this experiment is to record and compare the input and the output waveforms of a half-wave rectifier, a full-wave rectifier, and with the capacitive filter attached in both cases. The apparatus used were 12-volt transformers, oscilloscope, digital multimeter, project board, 1N4007 diode, 10 kΩ resistor, light emitting diode, and capacitors of capacitance 22 microfarad, 47 microfarad, and 100 microfarad. This is the result of our experiment. In part 1, half-wave rectifier circuit, the VRMS of channel 1 was 9.7 volts, while VRMS of channel 2 was 6.7 volts. In part 2, a capacitive filter was attached to the half-wave rectifier. For every capacitor, we measure the VRMS in DC coupling mode, then peak-to-peak voltage in AC coupling mode. Part 3 was conducted on a full-wave rectifier. The VRMS of channel 1 was 9.7 volts, while VRMS of channel 2 was 9.6 volts. Similarly, a capacitive filter is attached onto the rectifier in part 4. We then measure the VRMS and peak-to-peak voltage for each value of capacitance. The next is analysis for part 1. The image of the bottom left was a picture of input and output of a half-wave rectifier. The yellow line was the input while the cyan line was the output. We observed that the negative half cycle of the input was clipped by the diode and produced a horizontal line on the output. The frequency of both input and output signals are 50 Hz. The theoretical channel 2 VRMS is half of output peak voltage. The percentage error is 3.08%. In part 2, 3 capacitors of different capacitance were attached to the half-wave rectifier circuit. The time constant of the filter tau is the product of the resistance and capacitance. We can see that the peak-to-peak ripple voltage is the lowest for 100 microfarad capacitor filter. The formula for DC output voltage is equal to 2 times output VRMS minus peak-to-peak ripple voltage divided by 2. Starting from the left, we have the input and output voltage of the circuit with 22 microfarad, 47 microfarads, and 100 microfarad capacitors. The output voltage rose sharply on every positive input peak, and then drop for the rest of the cycle. The percentage error of DC output voltage for the first two capacitors were negative 0.31% and negative 0.99%. However, the result of 100 microfarad is 0 volts, but the theoretical value is 13.27 volts, resulting in a negative 100% error. In part 3, 2 diodes were connected to the center tap transformers. From the picture of oscilloscope, we observe that the negative half cycle was inverted by the rectifier. The frequency of the output voltage was double its input at 100 Hz. The formula for output's VRMS for the full-wave rectifier is output peak voltage divided by the square root or 0.707 times output peak voltage. The theoretical value of output VRMS is 9.2 volts. The percentage error is 4.75%. In part 4, the time constant is the same as the setup in part 2, except the rectifier was full wave. We observe that the peak-to-peak ripple voltage was about half of that in part 2. The formula of DC output is equal to the square root of 2 times output VRMS minus peak-to-peak ripple voltage divided by 2. The shape of the output voltage wave is similar to those in part 2, except the sharp rise occurs at the peak of negative half cycle as well. The measure of output of our experiment was all 0 volts, which is negative 100% error compared to theoretical values.
The input frequency from the transformer was 50 Hz for all circuits. The output frequency for Part 1 half-wave rectifier was 50 Hz. In a half-wave rectifier circuit, for the positive half cycle, the diode was forward biased. There was a voltage over the resistor. During the negative half cycle, the diode was in reverse bias. There was no voltage over the resistor. Meanwhile, the output frequency of the full-wave rectifier was 100 Hz. During the positive half cycle, diode 1 was forward biased and there was a positive voltage over BC. During the negative half cycle, diode 2 was in forward bias. There was a positive voltage over BC as well. Negative half cycle was flipped to positive, doubling the signal frequency. The time constant tau of the capacitive filter of 22 microfarad, 47 microfarad and 100 microfarad capacitors were 0.22 seconds, 0.47 seconds and 1 second respectively. The voltage of the discharging capacitor is equal to V0 times the exponent of negative time per RC or tau. Substituting the time with the period of output signal for part 2 and 4, and we can get the percentage of voltage discharge at the end of every cycle. From the table, we can see that the voltage discharge decreases as capacitance increases. This is related to the peak-to-peak ripple voltage of the filtered output. Ripple voltage decreases as time constant increases. We can also compare the voltage discharge between the half-wave and full-wave rectifiers. The value for full-wave rectifier was half of its half-wave counterpart. When the period of the wave is much smaller than the time constant, the slope is close to linear. This means that when the frequency is double, discharging time is half. The voltage discharge and the ripple voltage is also half. The LED is dimmest in part 1 and the brightness increases with increasing capacitance. We can infer that the DC equivalent voltage is high when the rectifier output passes through a filter with high time constant. The DC voltage level of a signal is its average voltage. The average voltage of a half-wave rectifier is the peak output voltage per pi, and for full-wave rectifier it is twice of that. In terms of VRMS values for my experiment, the coefficients are 0.637 and 0.9 respectively. The output VRMS for part 1 was 6.7 volts and part 3 was 9.6 volts. The DC voltage is calculated to be 4.3 volts for part 1 and 8.7 volts for part 2. We are able to prove the ratio between the two DC voltage levels. Comparing the brightness of LED between part 1 and 3, we observe that the LED in part 1 is dimmer than the one in part 3. This means that the half-wave rectifier supplies less power compared to a full-wave rectifier. Power factor is the ratio between DC power and AC power. Conveniently, we only have to square the coefficients we got from the last slide to get the power factors for half-wave and full-wave rectifier. The relationship between half-wave power factor and full-wave power factor are also the same.
A rectifier is a circuit that converts an AC input into a DC output. It uses one or more diodes to limit the direction of current to one direction. In our experiment, channel 1 was set to AC coupling, which means that the wave was centered at 0. Channel 2 was set to DC coupling, which means that the DC bias was not ignored. This is important because we wanted to measure the DC voltage output. The percentage error of output VRMS for part 1 and 3 were small, at 3.08% and 4.35% respectively. The error in part 1 is because the rectified negative half cycle was not completely flat. The oscilloscope calculates the true RMS of the wave and included a small leakage during reverse bias. The error in part 3 may be due to the near around 0 volts. The near around the junction voltage of diode is nonlinear. The signal was distorted and rounded when it approaches 0 volts. In part 2 and 4, most readings of output VRMS were 0. The main reason was that RMS is not a measure of DC voltage, but AC voltage. Although in theory, the filter VRMS should approximately be the same as the average voltage, but since the oscilloscope measures it to be 0, we suggest that in future experiment the average is taken instead. From our pictures, the average voltage shown on the oscillator agrees with the theoretical values. Here's a short proof on how the filter VRMS is close to the value of the DC voltage or average voltage. The blue line is the input signal and the red line is the filter signal. The ripple voltage is small compared to the output peak voltage. Since the period is much smaller than the time constant of filter, we assume that the filter wave is a sawtooth wave. The RMS of a sawtooth wave is its peak voltage divided by square root 3. For a DC bias sawtooth wave, the RMS is the square root of the sum of two RMS values squared. The RMS of VDC is VDC and the RMS of the ripple voltage is peak ripple voltage per square root 3. The peak ripple voltage is derived from the peak to peak ripple voltage we measure. In terms of output peak voltage and output peak to peak ripple voltage, VRMS is equal to this. You can see the effect of ripple voltage on output VRMS is very small. When you look at it logically, a signal that approaches a constant voltage will have a VRMS of that constant. There are a few common applications of rectifiers in our daily life. First of all, rectifiers are used for powering appliances. The use of a half-wave rectifier can help us achieve the desired DC voltage by using step-down or step-up transformers. Full-wave rectifiers are even used for powering up the motor and LED, which works on DC voltage. It is also used in AM radios as detectors because the output consists of audio in the form of electric signals. Rectifiers are also used in firing circuits and pulse-generating circuits. The reason the DC output from rectifier goes through a filter is because it has a large ripple voltage, the same magnitude as output peak voltage. Ripple voltage is undesirable in DC operated circuit. It reduces the DC equivalent voltage of rectifier output. It also induces heat due to parasitic inductance in electronic components reacting to the changing current. A filter is important to reduce the ripple voltage to a manageable amount before sending it to a voltage regulator. In conclusion, a half-wave rectifier clips the negative half cycle of input, while a full-wave rectifier inverts it. The output frequency remains the same for the former but doubles for the latter. A capacitive filter smooths the rectifier output and reduces the ripple voltage. The higher the time constant, the lower the ripple voltage, the higher the DC voltage. The ripple voltage of full-wave rectifier is half of half-wave rectifier when both have the same time constant. These were our references for this report. We hope we did a good job on explaining our experiment. Thank you!